Also, you have this exercise for how to find it for ft equal to sine omega t ut and ft equal to cosine omega t ut. All the answers, I mean, for this exercise, you can find it here in this table. Okay, so this table actually summarize the most commonly used Laplace transforms. It gives you the function and then what will be its Laplace transform. Function, what will be its Laplace transform, and so on. For all this function here, later on this function will be used directly to find the Laplace transform for some other functions. I mean, maybe you have some combination of 2 or 3 function of this one, so you can find what the Laplace transform for the overall function. Also, this table will be used in order to find the inverse Laplace transform. So if you already have the Laplace transform, which is 1 over s plus 5, for example, you are going to use this formula to find what is the inverse. The inverse will be, if this one is 1 over s plus 5, that means the integration or the inverse of it will become exponential negative 5t. If this one 1 over s plus 2 all square, so that means its inverse will be t exponential negative 2t, for example. I mean negative 2t here. So I mean these formulas will be used later on just directly in order to find the inverse Laplace transform based on this table. So what are the properties of the Laplace transform here? So here some of the properties that will be applicable for Laplace transform calculations, and we can benefit from them in order to simplify the calculation of Laplace transform for complicated or complex functions. So instead of have one function which I can easily find it in the table, I may have some of complicated function which combine between 2 or 3 or 4 parts, and I need to simplify to use the table directly to find their Laplace and their inverse Laplace. So for example, the first property is linearity here. So the Laplace transform is linear. So that means when you find Laplace for x for ft, it's the same as when you find Laplace for a ft. For example, here you have a fixed number or constant multiplied by ft1, then constant multiplied by ft2, all there is a summation between them. Their Laplace transform also will be the same. It will be a1 times f1 s plus a2 times f2. Nothing changed. So you convert from time domain to frequency domain, and whatever is the number that you multiply by the function in the time domain, it will be multiplied by the function in the frequency domain. The same for scaling here. If you have if you have two functions here, there is you have summation, you have subtraction. You add, you subtract, and so on, plus, minus. So it will be applicable either in the time domain or in frequency domain. The same for scaling here. So if you have a number which is multiplied by the function, it will be directly reflected in its transform in the in the frequency domain. Either from time domain, f of at is equal to 1 over a, f of s over a, as we see previously in the table. Time shifting, if the function is shifted in the time domain, it also will be affected its value in that frequency domain by shifting in the frequency domain. So here, for example, you have Laplace ft minus a, ut minus a. That means when you multiply the function by ut minus a here, you shift it in the time domain. This shift in the time domain will be reflected in the frequency domain. So you have here exponential negative as times the function of fs. So the value of a here of the shifting times the value of the s operator will be shift in the frequency domain of the function. So later on, all these functions will be directly applicable to any similar form. If you have t minus 5, t minus 10, t minus 2, t plus 1, t plus 3, and so on, shifted in the time domain, you are going to see its effect here in the frequency domain. So as you can see here, This for the first function, for example, exponential negative a here. Then we have 1 over a s plus a. Then we go later here. If I multiply this function by operator, I mean by the variable t, so I will get square here. Here there is no t, so I just got the function 1 over s plus t. Then I multiply by t, I got square. I multiply by t to the power of n, for example, t square, t cubic, t to the power of 4, t to the power of 5. All this will be reflected here. So it's become like factorial of n, s plus a, n plus 1. So I mean, usually you are not going to get to find the same form exactly that you have in the table, but you need to think how the form that you will be given is similar or similar to which form of fs in this table. Okay, so if you have s, for example, if you have t square exponent here negative a t, so that means you are going to use this formula. So it's become, it will give you the transform here is will be 2 times or t here to the power of n. So you have factorial of n here. So it will be 2 times 1. So it will become like 2 over s plus a, n is equal to 2. So it becomes 2 plus 1. So it is 2 over s plus a or cubic, because 2 plus 1 here become 3. Okay, that means how you can benefit from this calculation in addition to the linear, I mean the property of the linear transform of the Laplace transform in order to use to further calculation. Later on, we have some example about this one. Then frequency shift here. That means if you shift the function if the function or the original function is shifted in frequency domain, that means fs plus a, you shift the frequency by magnitude of a. This should be reflected also in the time domain, which will give you exponential negative at ft ut. So you can see here the value of a that we use to shift in the frequency domain is reflected in the exponent of that multiplied by the original function in the time domain. Time differentiation here, for the derivative here, if you have d over dt, any function over dt, either, as I told you last previously, we said we may use this type of transform to analyze the AC circuit which has a capacitor or inductor and so on. So in that case, we are going to see this form d over dt. So each d over dt here should be converted into 1s operator. So if you have d square over dt square, that means the second order differential equation here. So this gives you s square. If you have d cubic over dt cubic, so this gives you s cubic and so on. So all this function here, the Laplace of the derivative of the function will give you s operator here times f of s minus this, we call it the initial conditions. And usually most time the initial condition are assumed to be 0. But if you given if you are given the value of the initial condition, so this initial condition will be used in such calculation. If I say the initial condition is f of 0 is equal to 1, that means you are going to add negative 1 here. If I said f of 0 is equal to 10, so you are going to have 10 in this equation. Same here, this is for the first derivative. The second differentiation here, it will be the same, s square. If you have the third or you have to the power of n, it becomes s to the power of n minus this is the I mean the transform, and here we have initial condition for the original function, initial condition for the derivative. Since you have multiple derivatives here, so you have the initial condition for n minus 1 derivative, initial condition n minus 2 derivative, until you reach to the original or to the function derivative initial condition. Another property is the integration here. So when you have Laplace for integration for the function fx dx, so this will be equal to 1 over s f of s. That means the value of x here dx will convert into fx, and you will add one operator 1 over s here, as we see before when we find the integration for ut function. We have 1 over s, then we have 1 over s squared, 1 over s cubic, and so on. So this s here, or this frequency operator, will be added to the function in the frequency domain in order to reflect the value or the power, the border of our integration. The same for the frequency derivative. If you have a function and you multiply by t, the function in the time domain, you multiply by t here, so it will give you the derivative of the function in the frequency domain. So Laplace t of t is equal to negative dfs over ds. So that means this function here, if you want to find the Laplace for, if you already have the Laplace for f of t, you find the Laplace for fs, then you add the derivative for this Laplace. In the case of, for example, I have ut here, I already find its Laplace transform is equal to 1 over s. Now I multiply t by ut. I want to find it, so I need to derivative for this one. So what is the derivative over ds for this one? It will give me 1 over s square here times exponential for the function here. As you can see, for tut, this is t. If you have the tut here, this one, it gives you 1 over s square, which is the derivative. It's like you drive this one in over ds. If you drag this one over ds, dfs over ds is equal to square of the denominator here, denominator times the numerator minus numerator times the derivative of the denominator, which give you 1 over s square. So this square, then s times the derivative of 1 is 0, minus 1 times the derivative of s, which is 1. So it gives you 1 over 1 s squared. I mean, these functions, or these properties can be easily compared when you refer to this table. Then the time periodicity here, we see the function can be considered, if you have the function is periodic function, which is repeated every time. So the value of the Laplace transform for the first function, which equal to, the first shifted function or the original function over 1 minus exponential negative ts. So all these function, if you have if the function is repeated every specific time period, so its transfer function will equal to the original one, or the period or the function of number 1 over 1 minus exponential negative ts. So this is the value of the period that will be affect your Laplace transform for this function. Initial and final values. Also, this is some of the property of the Laplace transform. So if you have you want to find what is the initial condition for the function ft when t equal to 0, or t goes to 0 here. So it equal to the limit when s goes to 0 to infinity for s fs. So what you need to do, if you want to find the value of f of 0, but by using the Laplace transform, you need to find the value of this limit, s go to infinity, s fs. That means ft, you convert it into fs, then you multiply by s, then you substitute for each s by infinity. Why we need to do all these things? Because the function in the time domain will be more complicated when we talk about the differential equation, or we talk about the second derivative or third derivative and so on. The function in the time domain become more complicated. So how to make it easier to calculate, as we will see later on in the examples, we need to convert it into the frequency domain. Then we find the limit for s equal to infinity. We want to find the limit for the function, limit t go to infinity for ft. How to find it? I convert this ft into fs, then I find limit s goes to 0 for sfs. So whatever is the functions that you have here in this table, for example, if we said what is the initial condition when for ft equal to t, when time equal to 0. So the initial condition for this one, because it's simple function, is equal to 0, for example. But if I want to find it in term or by using Laplace transform, I'm going to find limit s goes to infinity s times fs, which is 1 over s squared. So this square with that s, so I have 1 over s. I substitute here s equal to infinity, so it gave me 0, the same initial condition here that I have. I mean, either you find it by using Laplace form in the frequency domain, or you can find it by using time domain. But sometimes, if you want to analyze the circuit by using time domain, it's become more complicated. So the easier way to find it is to use Laplace transform, as we are going to see later on when we use Laplace to analyze the circuit, I mean the electrical circuit. So this is how to apply Laplace for the derivative here. It's more as I already mentioned before. So I said if I have Laplace for the first derivative here, dx over dt, it will convert into s times xs. Then we have here initial condition, and we said mostly initial condition are equal to 0. But if you provided with initial condition, you need to consider in your calculation. Laplace d square xt over dt square. I will take this d square over dt square, all this will become s square. Then xt become xs. This will be my answer, s square xs. Okay, then the rest here represent the initial condition. Since I have the second derivative, so I have initial condition, the original one, which is x of 0, and initial condition for the first degree derivative, or the first derivative, which is dx over dt 0. This condition usually 0, but sometimes it will be given, so you need to consider. The same here when you apply it in general, so it become like dn over dtn here. It gives you s to the power of n. Xt in time domain, want to convert in frequency domain, it's become xs. Then the rest here, which is starting from this point until here, represent the initial conditions. This is the table that summarizes the most or all properties of the Laplace transform, starting from the linear definition here, then linear theorem, frequency shifting, time shifting, scaling, derivative here for the first order, second order, I mean first degree, second degree, third degree, and so on. Then you go for integration theorem, final value theorem, and initial value theorem. All these formula you can directly use in order to calculate the different values of your Laplace transform for the complicated functions. So until here, any question? I think it is much easier for you now to go through these things because you already have the Fourier transform, which is more complicated, yeah? Should we proceed with the example or not? You still here or you already go for lunch? I don't like this time for teaching, but what? Shafiq, you still here?
Yes.
Okay, okay. Just I need at least one student in the class, okay? Since Shafiq is here, so just continue. Hadi, still outside?
Yes, sir.
Okay, okay, good. Okay, so for this example here, find the Laplace transform for this function, which is ft equal to delta t plus 2ut minus 3 exponent negative 2t ut. So if you go back to the table that we have, so you can find some similar form. For example, delta t, we already find what is the Laplace for it. We said it's equal to 1. We have ut also, we already find that it's 1 over s. Then we have here 3 exponential negative 2t. Also, we have some similar form of it. Now, our task, how to benefit from this information in the table in order to find the overall Laplace transform for this combination of functions. Okay, so the first way here is just apply the linearity property. Linearity, that means ft for, if you are in the time domain, the functions are add or subtract, either plus or minus here, you can just convert the same or apply the same in the frequency domain. So this function consists from multiple parts, so you just let it in multiple parts in the frequency domain. So it becomes like fs equal to Laplace for the whole functions. Then you distribute Laplace for each function separately. So you find Laplace for delta t, Laplace for or 2 Laplace for ut here. Then you have 3 Laplace for exponential negative 2t ut. Okay. Then from the table here, you go this one, you find it is equal to 1. Then 2 Laplace ut, it becomes 2 over us, this part, second part, which is here. Then the third part, which is 3 Laplace exponential negative 2t ut. Here you can find it also from the table, which is for the exponential of negative 2t here is equal to 1 over s plus 2. You can find it from this formula here. This exponential negative 2t, for example, it's become 1 over s plus 2. If it is exponential negative 2t, it's become 1 over s plus 2. If it's exponential negative 3t, so it's become 1 over s plus 3 and so on. You just substitute for the value of a here. So here we have 2t, so it's become 3. This is constant. Then 1 over s plus 2. This is the value of a in the table, which is equal to 2. Okay, so now you can compile all into one function, which is you take s plus 2 as a denominator, common denominator here. Then you find what is the numerator of your function. So this is the the common method that we use in order to calculate our Laplace transform. You see, we don't need to find the integration from 0 to infinity for all these delta t plus 2ut minus negative minus 3 exponent 2t ut, all delta t. Times exponential negative st or delta t, because it's become more complicated when we use the integration form. So the way that we use to calculate the exponential in the case of the combination of multiple functions, we are going to use the table of formulas. So table of formula, we are going to convert each part and we apply the sum of the property of the Laplace transform to make it easier to find the Laplace transform. Because our aim is not the mathematical calculation for Laplace. Our aim is how to use Laplace in some application in circuit analysis. Okay, so how to use Laplace to find some values in the electric circuit, how to use Laplace to solve some differential equation which is related to electric circuit. Okay, it's more on the application of Laplace transform rather than the calculation of Laplace itself. Another method here we can use also to solve this. There is another example here we use to find the value of the Laplace here. So find the Laplace transform for the gate function. I gave you the gate function from 2 to 3 and the value is equal to 10. The first you need to do here, how to convert this function from drawing or from graph into a function or into a mathematical function. How to write the value of gt here. We have the function, we call it gt. How to write the function of gt here. After you got the gt, it is easy to find the value of gs, either by using the integration, if it is a simple calculation, or use the table in order to find the different part of this function. So how to write this gt here? Gt is equal to, actually it is a unit function. Unit function means it's like is define some constant number, but it has here border, because the ut here, the normal ut, we said start from 0 until infinity. It's open from 0 to infinity and give you the value of 1. If we have 10 ut, it gives you the value of 10, but also from 0 to infinity. But here it is limited to this part. Since it is limited to this part, so you need to define it is ut minus 2. That means ut minus 2 minus ut minus 3. So this is how to write the function. Shift from 0 by 2, and the other one is shift from 0 by 3. And our function is the difference between them, difference between 2 and 3, between ut minus 2 and ut minus 3. So after we write this function, also we have the magnitude here. It is ut, yes, but it is not just 1 ut, it is 10. So it is 10 ut minus 2 minus ut minus 3. Okay. After that, after we have this function now, we need to apply some of the Laplace transform property in order to find what is the inverse, what is the value of Laplace for these functions. So what is the property that we need to apply here? We can apply the time shift, because in the time shift property here, as we can see here for the time shifting property, we said Laplace for f t minus t is equal to exponential negative st fs. That means fs here is the Laplace transform of ft only, and in our case here ft is equal to ut. But in the shift here, the exponential here will be the shift that we have calculated for this value. Also the same here, the time shifting, this frequency shift, this is time shifting here, Laplace for ft minus a times ut minus a, it will give you exponential negative a. This is the value of the shift. You see here, this is the value of the shift. So exponential negative a s, here fs represent the Laplace transform of ft itself. Whatever is the value of ft, is it ut, is it delta t, is it ramp function, sinusoidal, whatever is it. So I find its Laplace, then I multiply by exponent negative as. A represents the shift in the time domain, and S here is the operator of our Laplace transform. So we can see here, we have the value 10 is constant, still there 10. Then we have the first part. What is the Laplace for this part? ut minus 2. Ut, we know the Laplace for ut is equal to 1 over s. But if we want to have ut of minus 2, that means it has the value of a is equal to 2 shift in the time domain. So in this case, we are going to multiply by exponential negative a, which is 2s here. So our a here is equal to 2 based on the main formula that we have. Then we need to multiply by exponential negative a. If we just find the formula here, we said Laplace for f of t minus a will give you the value of e minus as times fs. So what is the value of a here? Is that the shift in the time domain, which is 2 in this case, which is 3 in the other case. And what is the integration or the Laplace transform for ft itself? Ft is a ut here. So I have a ut function in both cases. So the value of fs is equal to 1 over s. So you can see here 1 over s here, 1 over s here. This, the top here value, which is exponent negative 2s, exponent negative 3s. A here, this one is the value of a in the first function. This one is the value of a in the second function. So in the first function, a is equal to 2. In the second function, a equal to 3. And this is the s operator that we have in the original equations. So it gave me this one, these values for times 10, because 10 is a constant number here. So I can simplify 10 over s because s here is common. So I just take it outside. 10 over s, I still have exponent negative 2s minus exponent negative 3s. So this is how we can use the linear, I mean the time shift property of the Laplace transform in order to calculate the value of Laplace transform for a complicated functions. Is it clear here or not? Any question about this part?
Yes, sir.
Clear? Okay, thank you. We have another method here we can use to solve by using different another property. Here we use the time shift property that we learned. Okay, then we can apply another method which is we call it the derivative. So derivative, that means I have the function, I am going to drive this function into its derivative. Then based on the derivative of this function, I can use the derivative property of Laplace to find it. You are not required to apply all properties. So but here just to show you that all method can give you the same, or all properties can give you the same Laplace transform values, I mean function. Okay, so this is the original function, which is gt is equal to 10 between 2 and 3. As we said, it was like ut minus 2 minus ut minus 3. So this was the original function. I want to drive this one, so we go for the derivative of gt here. The derivative of gt in this form will give you these two functions, which is impulse functions. So the impulse function here, you have impulse function at the point 2, and you have impulse function on the point 3. The first impulse function is all are multiplied by 10 because you have the value of the pulse here, 10 either in the positive side or in the negative side. So when you apply the derivative here, it's equal to 10 delta t minus 2. So the delta here, the original impulse function is at 0, but in this case there is no shift, there is no time shift, but here we have time shift is equal to 2. So it is t minus 2. So 10 delta t minus 2 minus 10 delta t minus 3, the other one. Okay, so because you have here, you drive this part, then you drive this part will give you positive 2, I mean 10 delta t minus 2, this negative 10 delta t minus 3. After you drive this, I mean, you got the derivative here, you can apply the Laplace for the derivative. So the formula said if you have d over dt for any function, this d over dt can convert to 1s if the first derivative. Since we have 1 prime here, so that means this is the first derivative, so you need to multiply the function by only 1s. So you have s times gs, okay, because we have d over t for gt here. So gt become gs and d over t become 1s, or s to the power of 1, okay, when we apply the derivative theorem. Minus g of 0 here, g0 here represent the initial conditions, okay. So the initial condition here, we assume the initial condition is equal to 0. So you just substitute for the value here, s times gs, which is gs here, the exponential negative 2s minus 10 exponential negative 3s, because this represent, I mean, sorry, the delta here, this part give you this from the table. We said delta t gave you 1, but delta t minus 2, it will give you 1 times exponential negative 2s. This because it is shift or time shift. Okay, it is shift in the time domain. It's shift by the time domain. That means you need to consider to add exponent negative 2s. So this is the derivative of the first function. This is the derivative of the second function, which is 10 exponent negative 3s. Okay. So SGS again will give you 10. Then you simplify this one. If you want to find GS, which is the Laplace of GT, you need to divide over s, so it's become 10 over s exponent negative 2s minus exponent negative 3s. It is the same value that you have in this case. So I mean, this is just to show how you can apply the different property of Laplace in order to calculate the value of Laplace transform. The method 3 here, you can use the equation of the definition that we have before, which is integration from 0 to infinity for gt exponent negative st dt. This is the original formula. So at the end, you need to apply here. If you have the formula or the function is from 2 to 3, so you need to apply the integration from 2 to 3 as well, because otherwise here all 0. Everywhere it is the value is 0 of our integration. No benefit from find integration for a 0 value. So we only have the area under this rectangular here from 2 to 3, and the top here is equal to 10. Okay, so it's 2 to 3, 10 exponent negative st dt. That means the value here is 10. So I just put the value is 10. This the value or this operator of the integration that we have. The value of gt is equal to 10 from 2 to 3. Then dt, you integrate this one, you got it same, this go out, integration 2 to 3. This the integration of this value is equal to e negative st over negative s. Okay, so the same here, this is the negative s, and the operator terminal is from, I mean the integration from 2 to 3. You substitute, one time is 3 for the t, one time is 2 for the t. You got, when you substitute for 3, so it's become like negative 3t. For 2, it's become negative 2s, 3s, and this is the negative s here, will go out, I mean, will become 10 over s value here. This not 2, this 10 over s, according to this one, 10 over s. Okay, so just correct this one in the slide. This 10 over s exponent negative 2s minus exponent negative 3s. Clear? That means you have many options or multiple options to calculate the Laplace transform. You can calculate it directly from the integration form. You can calculate it by using any of its properties. Okay, either for derivative, either you limit, I mean for the, in the case you have limit values, or I mean go to, the values go to infinity, or the value go to initial condition and so on. So you can select the one that is more proper or most easier for you to use in your calculation. At the end also you have the table of formulas. You can use the linearity function, you can use the time shift, you can use the frequency shift in order to calculate the Laplace transform by using its or the table of formulas that you will be provided. So the same here, this one exercise, you can try for this exercise, okay? And you can, after you solve this exercise, you just, you solve this exercise in a piece of paper, and you can text either in group or in Kalam. I don't know. I will make this one in Kalam, okay? I will make this exercise in Kalam, then you can upload your answer for this exercise. This exercise for you, you can do it, you can answer.